do this backwards, I feel like I would put the arrow going up into A from B, like, below it. Does that make sense?
Right. Which one would you put up?
Oh, from, normal.
That you'd put,
Like I would.
oh,
put
you'd have that one flipped?
I would have the arrow going up, but I would have it like underneath the A.
Oh, you would draw it here.
Yeah. Is that still wrong?
No, as long as it's clearly not associated with this one. If you drew it in the middle right there, and I have no idea which one you're trying to draw it on, but if you're drawing it there, I'm perfectly fine with that. It makes more sense to draw it there than there, but
I just wanted to make sure
ultimately,
they were still right.
no, that's fine, because I can clearly see that there's a difference between those forces and these forces. And it automatically changed to green. Look, and back to pink. All right, so. The scale. It's a scale, analog scale. Needle goes back and forth. I step on the scale. What does the scale measure? It does not measure weight.
Gravitational pull.
It does not measure that either.
Or like,
Mass?
Nope.
Pounds.
First off, balances measure mass, scales measure forces.
Measures your force, or not your force, your
It's measuring some force.
Gravity's force on you.
How would you, is that different from weight or force through gravity? Or gravitational force, whichever one you said? Jacob said. Well, let's do a force diagram. I'm gonna draw with three objects. I've got absolutely spectacular stick figure. I have the scale, and I have the ground. Force diagram should look almost identical to what we had before. I'm going to change subscripts, but I got a person here, so I got weight of person, weight of person, weight of scale, weight of scale, normal force acting on person, normal force acting on person, or from person acting on scale, and then there's this normal force up on scale and normal force on earth. So, what does the scale actually measure? Let me change the wording. What force is the person exerting on the scale? What forces are acting on the scale? Let's do it that way. What are the forces acting on the scale?
the weight from person.
Where's that going to drop?
The weight from the scale.
Okay, weight of the scale is acting on the scale. That's this force right here. What else?
The normal force of the person to the scale.
That one right there. That one. And
The normal force of the scale.
okay. What is the force the person exerts on the scale?
The normal force of the person.
That is the force the person exerts on the scale, which would be equal in magnitude to that. I'm assuming that all of you have stepped on an analog scale at some point in your life. You've seen the dial go back and forth. When you first step on it, does it go immediately to your weight? What does it do? Typically it goes past and then comes back and then settles in. If I step on a scale really hard, I can get that pegged up thing to like 300 pounds. I don't weigh 300 pounds. That is not the gravitational pull on me. My stepping on the scale does not change my weight. But I can bounce on a scale and then the dial is going back and forth like this. My weight's not changing just because I'm bouncing on a scale. The normal force is what the scale actually measures. Now, if I am standing on the scale perfectly still, my acceleration is 0. So if the acceleration of the person is 0, then the total force on me is 0. Which means that the normal force up equals the weight acting down. So if I am standing on this scale, not accelerating, then my normal force is equal to my weight in magnitude. And then that's why we call it measuring my weight, but really it's measuring the normal force. Because again, if I'm bouncing on a scale, my weight's not changing just because I'm moving. But the scale reads changes. All right. Any questions before we do box on ramp? It's box on ramp time. Ramp. Box. Now, if you'll notice in this, when I drew my ramp, I don't have anything between ramp and ground here. This is to indicate that the ramp is part of the ground. If I wanted the ramp separate, well, we can do that separately, but if I wanted to draw it separate, I would actually draw the wedge, not part of the ground. So I have two objects here. I have the ground, which happens to have a ramp in it, and I have a box. So first step,
Separate.
all right. I recommend when you draw the box, you draw it in the same orientation. That some students like to straighten it out. It's not inherently wrong, but students who do that tend to also have the normal force in the wrong direction. Oh, I forgot to put the title. We will do a bunch of box on ramp problems. All right, so can I get rid of any of these?
Tension.
Other.
Okay. We'll say friction for last since that's the new one. Gravitational force. Which way is gravitational force acting on the box?
Down on the box.
By definition of the word down. Oops, sorry. It's close enough to the planet, I can use weight. And where do I draw my up arrow?
Up on the ground.
Yep. Now, if you want to draw it out here or where the wedge is, it really doesn't matter where you draw it because this is all one object. Somehow making it clear that it's part of that force, the force acting on the ground. Sometimes I'll put it directly underneath, sometimes I'll put it basically where the equivalent spot is there. Done. Normal force. Which way is normal force acting on the box? Let's see if people will commit rookie mistake number, whatever we're up to.
It would be up on the box in the direction that the ground is.
So up and right? that what you're going for?
Yes.
You didn't sound confident.
I know.
Say it like you mean it.
Yes.
The most common mistake I see here is people who get into this idea that normal force is always the opposite of weight. No, it's not. Normal force is perpendicular to the surface. Just in all the other problems we've done so far, the surfaces have been horizontal. But we have a normal force acting that way. Where's the other part of that pair? Acting on
The ramp.
Okay. I have only two objects, so when a normal force pair done, friction. If the ramp were frictionless, which way would the box move?
Down the ramp.
So friction says, no, not on my watch, as best as I can prevent that. So friction wants to oppose that motion on the box or the ramp.
On the ramp going upwards?
On the ramp going up, so down on the box,
Uh,
or down that way on the box?
I thought it was gonna be on the actual ramp going.
Well, there will be one on the ramp and one on the box.
It would be on the box, that it's opposing the direction that the box would go.
Yeah, the box wants to slide relative to the ramp. The box wants to slide down the ramp, and so it's going to act up the ramp on the box, and then down there. Questions? All right, so at this point, it feels like we should add some tension into it from a physics point of view, not just how we're feeling right now. So, I now have a rope. I have a pulley. A couple different things here. One, this is an ideal rope. An ideal rope has a couple characteristics. One, it is massless. It is frictionless. It is stretchless. Massless means I don't care about the weight of the rope. We assume, from a reality point of view, we'll be using string in the labs. The string, the weight of the string is not going to be, should not be significant. There will be a lab near the end where it does start to play a factor, but not a significant one. Frictionless, I'm not worried about forces acting on the rope to keep the rope from moving. We do bring friction into it in chapter 9? Somewhere after the second test, we'll bring friction into the rope. And stretchless, that A and B would move the same amount. And we're not going to have A staying still while B starts moving down the ramp. They will move together one way or the other. The pulley is ideal pulley. Ideal pulley is massless and frictionless. And deformless. We will bring in mass and friction later on. So a lot of physics is you start with some nice ideal simple examples, and then over time you start adding a little bit more reality, a little bit more reality to some extent. Now, a big question that some students get when they are faced with a pulley problem is the pulley separate from the ground? And so in something like this, when you get to the test level problem, probably there's gonna be a pulley in there. I guess there's a pulley in there probably 60% of the time. But with the pulley, I separate the items for you so you know what goes with what. So on this one I will do that. I've got A here. I have rope. I have B. And then the pulley is part of the ground. So any forces between the pulley and the ground, we don't need to worry about. Those are called internal forces. If you're going to worry about that, then that is a path to madness. Because if you're now worrying about the internal forces, well, you've got this box B here. What about the top half of box B versus the bottom half of box B? You're going to worry about those forces. Okay, if you worry about those, what about the lower right quadrant versus the lower left quadrant versus the upper right quadrant versus the upper left quadrant? Well, we can break that up even more. We can get down to the atomic level. How are the atoms interacting with each other? Thus the path to madness. So internal forces we're not worrying about. Okay. Got my checklist. We'll do tension last. Actually, we'll do friction last, because there's a comment I need to make about friction. Well, let's start with the easy one. Weight. Weight's acting on what?
Down on box A.
So I got weight of A, I got several objects here, so subscripts will be advised. And I got weight of A there, okay?
Down on box B.
Say it again?
Down on box B.
That's it. If you did a weight acting down on the rope and up on the ground, I would not take off for that. I would circle it just right again. Something that looks kind of like that, or ignore, and that just means I'm not going to worry about it. Officially, it is there, but we are assuming that it is irrelevant. It's an ideal rope, so technically it's massless, and therefore there's no weight. All right, normal force. Which way is normal force acting on B? So Y sub B and Y sub B. All right, and on A? Y sub A, Y sub A. So that's, oh, there's another pair of normal forces.
The rope in the pedal
The rope and the,
in the box.
oh, no, we're gonna call that tension.
Rope in the pulley.
Yeah. Something's holding the rope up, so that's this normal force. I got normal force, I guess subpar, and now the actual direction of that normal force, we really don't have enough information to know what that is. So just pretty much anywhere in that upward direction. Technically, it would be somewhere between the last point of contact and the first point of contact. So, somewhere in that range, depending upon what the angles are and the masses. All right, normal force done. Other? Tension.
On the rope in the box.
Which way is it acting on the box?
In the direction of the rope.
Yeah. So I have this FT, and then the other part is FT. And for B, similar. Do I need subscripts for the tensions? Is that a yes or a no? It looked like you were nodding, I wasn't sure.
Oh, no, that was my legs.
Okay,
No.
Yes, because you have two.
so it was a
pairs.
no and a yes? Ethan, you said no,
I said no.
and Jacob, you said yes?
Because you have two pairs.
Ethan, what's your argument for a no?
Because it's the same rope. And it's.
All right. Team Jacob, who says I need them? Team Ethan, who says we don't need them? A bunch of abstentions. You're both right. So, if you can put in subscripts, that is perfectly fine. If you're gonna put in a subscript, this would, like A and B and B. Absolutely nothing wrong with that. Check, move on. These are the ones that are opposite each other. These are the two forces of the pair. That's a different pair. If it is an ideal rope, it is going to be the same tension. Because there's no other force acting in the middle that's pulling it one way or the other. These are the only two forces that are trying to stretch it. So if it is an ideal rope, this tension and this tension are also the same, and so you would not need the subscripts. When we get to chapter 9 or whatever it is where we bring friction into it, at that point, we definitely need subscripts. But until then, optional. But if you're gonna do them, those are the pairs that have the same subscript. This pair has the same subscript. And now friction. Which way is friction acting on box B? So, Luis, you're saying up the ramp?
Up on the box, but yeah.
That way? Which way is it acting on A then? Do we leave someone else to answer that one?
Check.
Is that awesome? So they're both frictions are going that way? Is that what that last